next presentation is by Murray Hitzman of the Colorado School of Mines. He's going to give us a talk on mine mineral exploration geophysics for the future, from the perspective of an exploration geologist.
So thank you, Charles. Thank you, Ken. I'm probably the odd duck here. I don't represent a big, huge center with millions of dollars of research dollars. I come from a country which probably hasn't been up here in this session ever.
I don't know. That's a good question.
We missed you. In the United States, we produce a lot of minerals as well, but politically, our country doesn't think about it much, right? And instead, we just try and close it down. So, obviously, some of us do think about this a lot, who work with the industry, in the industry. And so my perspective will be basically personal. We are, at the same time, at my institution, trying to involve our government representatives, the USGS, with Colorado School of Mines. It's listed on the program that I'm representing, the Center for Mineral Resources. That's a new center which actually doesn't exist yet. We're hoping the legal documents between our school and the federal government will be signed sometime in the next month and a half. It's been going on for about 8 months so far. You know about lawyers in the United States, right? Okay, so you're going to see some of the same slides actually you saw from Mike, and some of the same reasons. This is from Richard Shoddy, who was here at the conference, and it really just goes through time. How do we find ore deposits? And the bottom line is obviously the prospecting is getting less because they're not sticking out of the ground. And even though it's hard to see, but the stuff on the bottom, the geophysics, while it's somewhat flat, I would argue it's sort of going up. And certainly geophysics plus geochem, I think the trend is clear. And this is exactly the same slide, redrafted slightly, from Richard Shoddy that was shown before. And there is a disconnect between dollars being expended and what we're finding, and that's worrying. And that's worrying for governments and clearly for industry. And the reason is, again, same slide, we're going undercover. It's getting deeper and deeper. And as it gets deeper, obviously, we have to think about different things. So, as we go forward, increasingly, I think the main technology will be geophysics. I don't think there's any doubt. So we need both better geophysical techniques and technologies. That's certainly not my expertise. I'm not a geophysicist. I don't invent hardware. There's a lot of people out there doing it. But we need to have better understanding of the geophysical properties of the geological materials.
Yeah,
and that is something that geologists should worry about.
Yep.
And I think traditionally we've worried about what the ore looks like. And I think that's been very short-sighted. What CIMIC's doing is obviously trying to extend that and get beyond that as well. So I think they're on exactly the right track. So we need to have integrated geological, geophysical models of ore deposits. And I think the CIMIC initiative is the first one I know of in the world that's really trying to do that. I'm involved in another one in Europe, which is just literally getting started in the last 2 weeks, where again, we're trying to do something very similar to what you're doing. And we're in the initial processes of trying to figure out our protocols, which is why I asked about the white papers. Okay, so geologists can help geophysicists with the data so we can develop the best tools. And one of the ways is better ore deposit models that actually work on petrophysics. So this is something that I worry about a lot.
Yeah.
So one of the models that I've sort of been known for a number of years is iron oxide copper gold. I taught a short course a couple of days ago about this. And this is a model that was put out about 10, 15 years ago in terms of alteration through time, or through space, right? And so there's, you can see a kilometer scale bar, 5 kilometer scale bar with these fancy names. And if you're a geophysicist, those names mean absolutely nothing to you, right? They're totally irrelevant. So, you know, as a geologist, I can put some things on there that might help a geophysicist a bit. I can tell them about some minerals that have geophysical properties, like hematite and magnetite, some other silicate minerals, and that might help a little bit. But realistically, nah, it's not enough. So, what we really need to do is actually measure the rocks. And this, again, CIMIC's doing some of this. We use techniques these days such as CAT scanners, or in my university we have QuemScan. And we do a lot of this already for geometallurgy or for mineralogy, petrology. But really what we need to do is do it straight for petrophysics. All right, so we're measuring the mineralogy, but we're actually measuring petrophysical properties at the same time. Again, CIMIC's trying to do that. We can do this now. We don't. CIMIC is one of the few groups, I think, that's actually routinely doing this. Most companies do not. Companies, the ones I'm involved with, we always do mag susceptibility, we always do density, right? And we put it in the database and it never gets seen again. The density gets seen by the guys doing a resource block model, but not the geologist. And mag sus, it just disappears, and it's there somewhere. Gee, we did that 10 years ago, where is it? What we need to do with the data is exactly what we do with the geochemical data, where we're routinely doing this with things like iogas, where we actually take it, do statistics, analyze it spatially, analyze it across different things, and it sounds simple, and it actually isn't that hard. I've done it in 1 or 2 projects, but it's still not done very often. Okay, the other thing we can do is develop better ore deposit models. And this is where I think most of the people in this audience are geophysicists, even though I know there's some geochemists working there too. But we should shoot ourselves because we're really bad at these. And I'm just as bad as anyone. So again, I'm going to turn to the IOCG model. And here's 3 different models from 3 different groups. And one of them, even though I didn't make up this slide, the last one, the metamorphic derived, would sort of be my model, I guess. The important thing to note, and the people who did these are all great geologists, fantastic geologists. One model predicts that we're actually dealing with a system that's 3 kilometers in depth, más o menos. Another system says that everything important is happening in 2 kilometers. And the third, the one I prefer actually, says it's 25 kilometers. That's a big difference. And that's a huge difference if you're thinking geophysically. Unbelievably different, right? My target size is totally different. So basically, the one point I'd need to make is we got to get our act together, right? We are not giving the geophysicists the data they need. So no wonder as geologists we bitch and moan about their black boxes and they never find anything, blah, blah, blah. But it's just as much our fault. And I don't think we take that on board. Okay, so we need better ore deposit models that provide accurate scales. That's an important thing. Scale is something really important in geoscience and especially in economic geology. Whoops, I'm going the wrong way. So here's a traditional IOCG anomaly that actually resulted in discovery. It's Prominent Hill, and it's typical for these systems. So the colored background is the magnetics. We can see we have a nice big anomaly here. And then the gravity is the contours, and we have an anomaly that overlaps the mag, and then this linear thing coming here. So of course what was done is they drilled right there and missed. And they drilled the highs here and missed. And it turns out the IOCG, like most of them in my experience, actually sits essentially on the shoulder of both. Okay? So somebody who has a whole bunch of experience, there's some really good geophysicists out there who've looked at lots and lots of data, and these days they'd probably pick the right places. Maybe we didn't for 20 years, but now, people might do it. But it's still not, this isn't good enough. So here's data from the Australian survey from the Gawler Kraton. They've gone out and done some really fantastic work. The Australians really should pat themselves on the back. And this is the mag and gravity anomalies. And so which one are you going to drill? Okay, Olympic Dam sits right there. Caravatina sits right there. Those are 2 deposits. There's a whole bunch of other things that look, to me, as good as those. All right? Remember, we have at least 300 meters of cover before I get to the anomaly. So this is a non-trivial thing. Juniors have been going out and basically systematically drilling these suckers. And it's expensive. So it's not good enough. And at Colorado School of Mines, where we differ from most universities in Canada or Australia, I think, and one of the reasons probably that we don't do as much mineral work is mineral companies are cheap, right? And the oil companies have a hell of a lot more money. So all our money comes from petroleum. So what we really do as much as anything is I work with petroleum guys. So this is the sort of look they have now at the subsurface. All right, 3D seismic. It's beautiful. We can actually see what's going on for real. And so somebody said, yeah, oil geology is simple, blah, blah, blah. Well, it is, but that's a bit messy. There's a couple of thrust faults in there. It's pretty torn up. But they can do some pretty amazing things. So 3D visualization of the subsurface is clearly where we have to go. And that's really sort of the bottom line. And we're doing it. So a number of people have talked about joint inversions of gravity and mag and going into the third dimension. And so that's sort of routinely being done probably for the last 5 or 6 years, mineral exploration, certainly in IOCG space. And this is just a random anomaly, which I won't say where it's from, somewhere in the Gauler Craton. And you can see that we can start to, this one is better probably than these couple. So that's good, that's limiting us a little bit. So here's Olympic Dam, done that way, 3D joint inversion model. And, again, which ones do I pick? Olympic Dam at this scale doesn't stand out as being particularly fantastic. The blue there is the magcess, and the red is what's interpreted as hematite. And remember, Olympic Dam's a hematite body. So, again, the Australians have gone out and done some really neat work. And they did 2 surveys that I think tell us a lot. And the data's been available for a while. So one is they ran a deep seismic survey over the top of the thing and tried to look to the bottom of the crust in terms of seismic reflection. And it's hard to see, but what they actually found is a whole bunch of reflectors, and then in these white zones, the reflectors all go poof, right? And there's no seismic reflection. So we don't know what that is, but we know the rock is screwed up. So the rock is probably incredibly altered somehow. The other thing they did was magnetotellurics, which is really what this stands out at. And that's what's being shown here, sort of the high response, right? And what you see is a big, huge anomaly, again, quite deep, right? And basically coming up. At the near surface, what they've put onto this image are basically all the 3D inversions of the gravity and mag. A number of which, Olympic Dam does go deep, but there's others that go pretty deep as well. But what's astounding to me is, I think it's better in the next slide, when I actually take all this data, now I can see the seismic, and you can see this bland area here. When I take the inversion, I take the magnetite model from the, basically from the MT, and the bland zone, I now have a unique point where all of these things meet. Right? And it just happens to be right at the Olympic Dam system. I think this is no coincidence. And the reason is the Olympic Dam system goes down to 45 kilometers. That's why it's one of the world's biggest ore deposits. Right? That is how big the system is. And that's what we have to get through our heads as explorationists. What is our target? If you're really looking for another Olympic Dam, you should be looking through the entire crust to find the size of the system. This is not what exploration companies are doing today, I can tell you, because I work with a lot of them. All right? Some of them say they're doing it, but they're not. All right? So again, stealing from the Australians, and we saw sort of another version of this before, this is exactly what we need to do. We still really are focused on that. That's our target. That's what we need to know. But what we really need to understand is the fluid delivery, and this is tens of kilometers, and the fluid exit, or the exhaust. And we probably really don't need tens of kilometers, because if it's tens of kilometers, we can't drill it. All right, so we have to think pragmatically. What realistically do we have to know on top? And my guess would be 2 kilometers at this point, right? Anything more than 2 kilometers, we probably don't want to find. Laterally, we need to think, again, in terms of at least 5, I'd say, clicks. So I need to understand what the petrophysical properties are of the rocks and all this. And CIMIC may be the first one that comes close to doing this, right? But we need a whole bunch of different examples from a lot of different ore deposit types. And I think we're going to be really surprised with the data that comes out. So I'm not going to go through this, I'm not a geophysicist, but just I'm trying to show sort of what is the range of techniques we can use in different spatial environments. And the point is that there are no silver bullets. So I think in any real exploration program, you shouldn't be using just one technology, one technique. That's really dumb. You always should be using 2 or 3. More expensive, yes, but that's how rocks work. So I think it's going to be really critical for geologists and geophysicists to work more closely together to develop forward models. So we have to go out and characterize real live ore deposits, but then certainly what I used to do with Chevron all the time, because it was routine in the oil industry, is I made up a synthetic deposit, and then we ran it through the computer and tried to figure out what the geophysical response would be with different technologies, before I ever went out and actually did something in the field. I think we need to be doing that all the time. And that's exactly what the petroleum industry does, right? With their teams of geologists, geophysicists, and petroleum and reservoir engineers. So we need to actually have better ore deposit models, that's us as geologists, that provide the real problems. And I think I have one more example here, yeah. So another one, this is again something that Mike's going to have brought up. Another problem that I've certainly faced in my career is, so we found the porphyries that stick out of the ground there. Now I have to find the porphyries that are under all this stuff, right? So how do I do that? Again, a non-trivial problem. And really the one is the one Mike showed. I think it's really cool. This is the same array in Long Beach, and while he said it's simple geology, it just so happens there's a couple of thrust faults, a strike slip fault or two, and a whole bunch of normal faults cutting through that section. It is really messed up. And it still worked, okay? Each of these cans, tin cans, they're about this by this, the actual seismometers, cost about 250 to 300 bucks. They're not expensive, right? So we can actually afford to buy a whole bunch of these. And you go out and yeah, you bury 5,000 of them, right? And you let them sit for, depending on how much energy you have, several weeks to a couple of months. In places like Chile, where there's lots of seismic energy as well as mine blasts, I think there's more than enough energy to do this. Now, what I'd be doing in this area is, I really, at the first point, I just want to know how deep the gravels are. That is an incredible seismic, the difference in seismic velocity between the gravels and the bedrock is huge.
Density also.
Yeah, so I can do that. There's no question. Even with passive, I can do it easily. We should be able to actually know the depth of gravels in Chile in every bloody basin in the next 4 years. Really cheap, if we wanted to do it. The real trick is, will passive seismic actually tell me, is there a velocity difference between sericitic alteration and unaltered intrusive rock? I don't know the answer to that. But I'm trying to get some of our geophysicists of minds just to think about that a lot, right? Because I think there should be a velocity difference. In which case, seismic might be a direct detection tool. No one ever really thought about that. Right? It might be brilliant, much better than IP or any of the others. Does that mean we wouldn't do IP or EM? Nope, you should absolutely do it. But this may be a whole other piece of the toolbox. Okay, and then finally, I actually want to step back even further, and this is the one that gets me in trouble when I talk to CEOs of companies. This is the way we mine today. And again, coming from the US as opposed to Canada or Australia, where you guys love big open pits and 10% of your economy, blah, blah, blah. In our country, we fill in all the coal mines, right, by law. And I wouldn't be surprised that in, certainly my students' lifetime, we're not going to be able to do that because society just won't allow it. So I think we really actually should be thinking about what kinds of mines we want 50 years from now. Because remember, if we find a mine tomorrow, it's probably going to take us 20 years to put in production. It's a big one, right? So we really need to be thinking decades out. So, that's my vision of the future. And this is also what I think the future is going to look like for mining. We're already doing it with some things like uranium, right near where I teach up in Nebraska. And we're starting to do it with copper down at Florence. It's been tried for about the last 30 years, but maybe now this one will get off the ground. And one of the reasons I really think this is again, from my background and what I do at mines, what we've been doing in mines the last couple of years is we help drive the fracking revolution. I know a lot of people from a lot of parts of the world hate fracking, think it's the worst thing since sliced bread, blah, 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 et cetera, right? I think it's dynamite. I think it's the environmentally best thing I've ever seen to get energy. Absolutely fantastic. But the technology to do it wasn't hard. It was just using a couple of things we already had in different ways, right? We took drilling, and instead of drilling vertically, we drilled sideways. And then instead of just stimulating a reservoir, we actually figured out how to actually control, break the rock around it. And then do a lot of microseismic to actually really prove what we're doing. So those technologies put together led to a total revolution. I mean, it's amazing to me that the U.S. is now the second biggest exporter of petrochemical, basically petroleum products in the world, right? Pretty neat. So, we actually should be developing integrated geological geophysical models now for the sorts of deposits we're going to need in the future. Things that maybe we could do in situ leach, or super high-grade deposits that might be much smaller, where a big company still would want to mine it, just because even though the tons aren't there, the value of the rock is so high that even BHP might be tempted to mine it, right?
Or the margins, yeah, right.
Yeah.
The margins may be so good.
So again, mineral exploration geologists and geophysicists must work closely together to develop these models of the many different and complex systems. And I think we also need to better integrate the tools we already have, as well as developing new tools and stealing shamelessly from everybody else. And as I say, we at CSM are trying to do this now with a joint venture with the USGS, with a new Center for Mineral Resources. The center will obviously look at economic geology, my interest. But the real hope is that we actually integrate with our geophysics department, which is electrical and seismic methods, but obviously a huge, or electrical and electrical methods, and our seismic group, and also our petroleum engineers who think about how to do things in the subsurface that most of us in mining engineering and mineral and economic geology don't. I think that's it. Thanks very much.
You mentioned petrophysical measurements, and you named mag susceptibility and density. What other petrophysical measurements are you talking about?
Talk to these guys. They're
They need to be done on a
geophysicists.
routine basis.
Conductivity, sonic,
Yeah.
velocities.
Reduce polarization.
Yep.
Yeah, and more and more we can do. You can do a lot of those things in very in the field.
Yeah.
Okay, yeah, a lot of those things you can do in the field. I mean, there's issues of QAQC, obviously,
Absolutely, gamma.
But
And spectral reflectance would come into that. It's kind of a hybrid,
Yep, technology.
more.
and even and that when we talk about petrophysical, but also things like X-ray fluorescence. The issues obviously are the homogeneity of the sample. There's a whole bunch of issues related to that, but
The other one's hardness.
Hardness.
Sounds funny, but no, hardness. How hard is the rock?
Hardness, yeah.
It's partially density, but it's slightly different.
yeah.
Yeah, Mary, what's interesting, this goes back to this idea of better linkages across the spectrum, is that Kid Creek has the largest microseismic system in the world, and they use it for rock
Bursts.
geotech.
Yeah.
Yeah.
They do not use it for exploration.
That's
No,
right.
no, they're right.
It's an incredible
Yeah.
story. And all the new mines that are open around the Sudbury area, they all have their own microseismic systems, run
Absolutely.
by engineers.
Yep.
And the potential is just huge.
Yeah.
Yep. Yep. Yes.
So you made some parallels with the oil exploration industry. I think there are a number of them, but certainly one of the big differences between hydrocarbon industry and mineral industry is where the actual costs come into the stream in terms of where you get your final product out.
No question.
In exploration in oil, it's all in the exploration. If you find something, it's relatively cheap to produce.
Except offshore.
Compared to the mining industry where
Yeah.
exploration is often the little bit front end and
Yeah.
the actual cost is the capitalization
Yeah.
to
Right.
get it
But,
out.
so let me say, my grandfather was an oil geologist, so it didn't used to be that way.
Yeah.
All right? He just went out and looked at hills and looked for anticlines and drilled them and was successful. So that's the way it used to be in the oil business, not that long ago, right? 2 generations ago. Our business is going to change, right? That's what I'm trying to say, right? We can't do what we've been doing if we're going to actually find what we need to find. So the business, if the companies can't adapt to that, they're going to go out of business. And their minds shut, they won't have anything else. Simple as that, right? The exploration part of the business is going to become more and more important. And it's going to become more and more expensive, period. Right? If you tell your bosses you can find it for cheaper, you're lying. It's going to take teams of people, which really in our business we don't really do. We say we do, but we don't. Right? We don't. Right? And in academia, it's really hard, even ourselves, to pull the teams together. This is non-trivial. And even in surveys, right? Because most surveys have a minerals group and an energy group, geophysics group and then a mapping group. And they don't talk to each other. And I worked for Chevron for almost 20 years, and not only did we talk together, we had the same darn office, right? We had to work together. That was the whole point. So we got to be more like them. They're successful.
Yep.
One of the things you mentioned, Murray, that I brought up, and we had a chance at a workshop in Vancouver a couple of years ago to, not to showcase, but remind people, and you mentioned the forward modeling, and I don't know if geologists in the room say, well, it isn't all about inversion and 2D or 3D and joint integration. In the beginning, when you're trying to get a concept of what you're looking for, a forward model is just say taking, this is a piece of geology in the earth, and I can ascribe attributes to it, a shape, a depth, a density, a susceptibility. And we've had the ability to generate what that would look like with our sensors for decades. And it's something that just seems to have been forgotten. But it's so cheap, and it's so easy to do, and it's a conversation that should be had when people are planning surveys. Can I see this deposit? If it ends up being a bowling ball, does anybody really want to go look for it? And if there's no signal. But if you don't engage the people that are actually got the concepts of the economic deposit you're looking for to come in and sit down and look at that, there's so many surveys, people go out there and they say, well, I'm hoping to find a Kidd Creek, but the chances of it, well, at 500 meters, yeah, good luck. That's just basically it. So it's important not to remember, it's important to remember that sometimes the early discussions in a planning process are so important. And they don't necessarily require rocket science. We've had a lot of this stuff around for a long time. You're probably talking about something in the 80s, but I remember when I came into the business, we had the USGS actually produced very good, they were Fortran programs, but they were very good forward modeling programs and some inversion. So.